We'll start the class at 7 o'clock. Okay, we'll start. Uh, this is the week 5 of the TA session of Design of Steel Structures taught by Professor Damodar Maiti. I am Trisha Chakravorty, one of the course teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. I'll start with a recap of the previous weeks. In the first week, we looked at the material steel that we are studying in this course. There are two broad branches of structural engineering: analysis and design. Analysis is the forward problem, where we are given the structural dimensions and the boundary conditions and the applied loads, and we have to find the response induced in the structure, the forces, the stresses, and the deflections and strains like that we have studied in structural analysis in second year. And the other aspect is design, that is the reverse problem, the inverse problem, where we will be given the loads that need to be withstood by the structure, and there will be certain serviceability criteria on maximum deflections and so on, and we have to find the optimum size of the structural elements. This is a course on design of steel structures. There are two major materials that we use for design: concrete and steel. Concrete is the most versatile material for constructions, and most residential buildings we see around us are made of concrete. So, why do we use steel? There are some advantages steel has, though it is very much costlier than concrete. Steel is much stronger than conventional concrete. That is, its yield strength in both tension compression is much higher. It has a high strength to weight ratio, so steel structures are generally lightweight, much more lightweight than concrete structures, and the sections of the beams and columns used in steel also have much lesser area than the concrete sections that are solid rectangles and have higher dimensions. And steel is also ductile compared to concrete. Its stress strain curve has it includes more area than concrete. That is how we define ductility, and we need ductility in design, because if material undergoes ductile failure, it will undergo a lot of strain. And even though the in stress capacity may not increase a lot, but as it deforms a lot, it will give a sufficient warning time for people to evacuate, and we want ductile failure compared to brittle failure. Brittle failure occurs very suddenly and it can lead to loss of life. And although we don't want to, of course, we design the structures to not fail at all, but under extreme loading conditions like an extreme earthquake, structures may collapse. And if it does collapse, we would prefer to save as many lives as we can. So, ductility is very important. And steel, as I said, is however much costlier than concrete. So still we see more concrete structures around us than steel ones. Steel is used in some specific type of structures like bridges, like truss bridge or suspension bridges, and in factory sheds, and especially in towers. In high-rise towers, we use steel because it has a greater strength. And why do we need design? When the components individually and the entire structure should withstand the loads throughout the lifespan, satisfying the serviceability criteria. The serviceability criteria have to do with deflection and the withstanding the load throughout its lifespan means it should not collapse. So that is the collapse criteria. There are two criteria which design a structure against: the collapse criteria and the serviceability criteria. And to properly design a structure, we have to ensure that it is economical to construct without compromising safety. So this is the most vital, the most important challenge that structural engineers face, that we cannot make a structure infinitely safe because the cost will become very high, but there is a certain level of safety that we have to ensure. So we have to ensure a cost effective design, and this requires knowledge of the design procedure in detail. And the design procedure is basically what structural engineers in India follow are the Indian standard codes. Similarly, all the countries have their own design codes that have a lot of research work behind the scenes, but in the codes, steps of design are presented in a simple manner so that any civil engineer can design them. Then we look at the mechanical properties. That some mechanical properties of steel that are listed in IS 800/2007, that is the Indian standard code for steel design. And these five properties, the code says that we can take these values irrespective of the grade. They are the density, that is 7850 kg per meter cube. The modulus of elasticity is 200 gigapascal, or 2 into 10 to the 5 megapascal. The Poisson's ratio is zero point 0.3. The modulus of rigidity is 0.769 into 10 to the power 5 megapascal, and the coefficient of thermal expansion alpha is 12 into 10 to the power minus 6 per degree centigrade. This is again relevant in not so much in concrete as in steel, because steel doesn't have a very high coefficient of thermal expansion, so that doesn't come into the design a lot. But in steel structures, it is important. And these are the two most important mechanical properties of steel, structural steel, that characterizes it, that is this grade. Irrespective of its grade, these five properties can be taken to be the same, but the yield stress Fy and the ultimate stress Fu are what defines the grade of steel. So the most commonly used grade of steel in the industry has yield stress 250 megapascal and the ultimate stress as 410 megapascal. It can vary, however. Yes, these are the rolled steel sections that have been standardized by the India IS code. The Bureau of Indian Standards (BIS) publishes the IS Handbook 1 that tabulates the properties of all these predefined sections. Unlike in concrete we size the sections of beams and columns. For example, beams, they have some criteria in the codes that the minimum dimension of a beam has to be greater than 250 millimeter, but it is not standardized. We can put it 300, 315, 350, any combination of the width and the depth of steels of beams and columns. Technically, even for steel structures we can do that, but mostly in the industry where we get the steel sections for, they are brought directly ready-made from the industry. They have certain cross sections, and the list of that is available in the IS Handbook number 1. It tabulates several properties like the weight per unit length, moment of inertia, the geometric dimensions, and other dimensions for various types of structures. This is an I section, a joist. This is a channel section or a C section. This is an angle. This is a T section. These are some of the sections that we use. These are some hollow sections and some solid sections. This is a stress strain, the elasticity curve, the stress. The stress versus strain curve, this is what characterizes the steel. This C or D is the yield point, and this E is the ultimate stress. So the stress corresponding to this CD that are very closely spaced are the Fy, and that corresponding to E is the Fu. And this curve we get by performing a tensile test on a cylindrical seal section. We take a cylindrical section, and we increase the tensile strength on it, and we note down the force that we are applying and the strain that is being developed in the specimen. So that gives us this curve. A is the limit of proportionality, B is the elastic limit. So up to A, this slope is the Young's modulus. E, that is said to be that we can take as 200 gigapascal irrespective of the grade of steel. Then from A to B, the behavior of the curve is nonlinear, but it is still B. Up to B, it is still elastic. That is, if we remove the stress completely, the strain will go to zero. But beyond B, if the specimen is stressed beyond the stress corresponding to B, there will be some residual strain or permanent set in the structure. At C and D, at these 2 points, around this point, the material yields. Yielding means that the strain increases a lot corresponding to the stress. Like here, the stress is increasing sharply as it is getting strained, but here it becomes much flatter, and where it starts behaving partially plastically. And E is the ultimate stress. After that, there is a decline in the stress even as we increase strain, and at F it fractures. This is the basic stress strain curve behavior of steel. The modes of failure in steel, unlike in concrete where we mostly look at bending moment and shear force, there are several other modes: bending, local buckling, shear buckling, web crushing and buckling, lateral torsional buckling, and deflection. And of these, buckling is one major addition from concrete, because this buckling occurs when a structure is slender, that is, uh, one dimension is much higher compared to the other two dimensions. So that is relevant more in steel sections because the cross sectional area is very less, and the height or length is much more compared to the cross sectional area. So buckling is an important criteria in several failure modes. And in week 2, we looked at the design philosophies, the working stress method and the limit state method. Limit state method is what IS 800, the 2000 revision at least, follows mostly. So in limit state method, we apply a factor of safety on the action or the load, and a factor of safety on the strength as well. And the basic equation that we have to satisfy is that the design action must be lesser than the design strength, and the factor of safety applied on the load is greater than 1, and the factor of safety applied on the strength is less than 1, or we say it is more than 1, but we divide the actual strength of the section we are using by the safety factor, so that we are applying the safety factors on both sides in such a way so as to make the design safer. And connections, now connections is the one of the most important topics in this course. So we have been looking at it for the past 2 weeks, and this week is also we look at connections. They are integral parts of any steel structures that have a major role in overall integrity, because the sections are brought from the industry and they have to be connected. They are not cast as a whole as in concrete. The standard parts are properly connected to create the steel structures, and the connections make up a large amount of the cost of structural seals. So they have to be designed very carefully. The two types of connections, the major ones are bolts and welds. As we have studied, that bolt has a shank and a head, and this the nut is used to tighten the bolt. So it develops the tension is developed inside this. So this is a good time to look at one of the doubts asked in the previous class, that why are friction type bolts high strength steel. Shrikar, I think you asked that, uh, if we can take a normal bolt and we can sufficiently tighten it, it will act as a friction type bolt, because in a friction type bolt, the basic force is not taken by the bolt material itself. Instead, it is tightly clamped, so that the two plates that we are connecting are clamped together, and the normal reaction transfer between the two plates is high, and so the friction developed, that is mu n, mu is the coefficient of static friction, is high enough to take the load. But in bearing and shearing type bolts, this friction is not taken into account, though there may be some friction. We don't take that into account, and we assume that the bolt material itself takes the load using shearing and bearing. Now he asks that why, even if we take a normal bolt and tighten it sufficiently, it will clamp the two plates enough to it to work as a friction type bolt. You are right that that does work, but there is one thing is that when you are clamping, what we are basically doing is we're pre-tensioning the bolt. Now, that is why the term friction grip bolt has become synonymous with high strength bolt. So because it has, the bolt has to have a high enough strength to take that to permit that amount of pre-tensioning. If that doesn't happen, the friction will fail. So it is not necessary that a friction that so it is not necessary that the friction type bolt has to be high strength, but it generally is for that reason, but it is not mandatory. If you can tighten a normal bolt enough to develop enough normal reaction, it will work as a friction type bolt. So in the IS code, it is not mentioned high tension steel bolts, though it is a commonly used term. It is written friction grip bolts when we design for friction grip. And the second type of connection is welds. That is, in weld we melt the parent material, and we there is a and the parent material, it's molten, and then it solidifies again, and it clamps the two plates together. Because there were also some other doubts from the previous class. Yes, one of those was, before I move on to eccentric connections. Okay, one of those questions was that why do we use in the design of butt welds we use Fy, that is yield strength, and in the design of fillet weld we use Fu, that is the ultimate strength. So in limit state design, technically we should be using the Fu in both cases, because the whole point of limit state design is that we exploit the post elastic behavior of the structure as well. But in butt welds, the special thing case that happens is that what we discussed last class is kind of true, that the butt weld is uh, this is a fillet weld. This is a fillet weld. In butt weld, the plates are placed end to end, and the welding is done in between the two plates. So that bolt is basically designed based on the serviceability criteria. Serviceability criteria means that when the strain increases, what happens after the post elastic behavior? Once the elastic limit is crossed, what happens is that the strain increases rapidly, but the stress doesn't increase enough. So the serviceability criteria, we always look at the yield stress. So for butt weld, we are interested in looking at the yield stress. We limit it up to the yield stress itself. But for fillet weld, it doesn't work like it. We don't need to look at that. We Yeah, for fillet weld, it's fine if we look at the collapse criteria, because even if the serviceability failure occurs, there is not much problem. But in the butt weld, if the strain is increasing too much, then the structural purpose will be defeated. So that is why we use Fy in butt weld, but Fu in fillet weld. And another question, we saw that in one of the worked out problems we looked at, the shear criteria was not checked in butt weld, but that is not correct. The shear criteria has to be checked. In a butt weld, shear and tensile strengths both have to be checked. And maybe in that question, the tensile one was critical, so they omitted the correct calculation of the shear stress, but you have to check that. However, in fillet weld, there is no possibility of any tension. So you can see that whatever the loading might be, this fillet weld has to fail in shear ultimately. So in the code as well, in the IS 800, for fillet weld you have to check only one criteria, the shear criteria, and for butt weld you have to check the both criteria, shear criteria and tensile criteria, and take the minimum of the two as the capacity.
Yes, thank you, ma'am, for the clarification. But I think will it be the same thing even in the fillet weld, even for the smaller like elongation, even in this situation, even the butt, however it acts, even for the
Yes.
smallest expansion or needle point, the
Yes.
fillet will also kind of uh, acts in the same way, because the displacement, how whatever is the small displacement happening in the butt while the load is applied, the same kind of displacement will be seen in the fillet weld also, I guess.
Yes, see, that is what my intuition also said, but I looked into a lot of discussions about this question, and they are all answering the same thing, that it depends on the load transfer mechanism, and based on, and the serviceability means the purpose for which the structure has been built, right? So in everywhere they say that based on the load transfer mechanism, you know what is meant by the load transfer mechanism, right? That how the load comes
Yes.
and it has to be transferred to the ultimate, to the boundary condition. That is the transfer.
Hmm.
So in butt weld, the serviceability criteria seems to become very important. So that is what
Okay.
of the reason is being cited now. I understand that we also have a little bit of problem in visualizing it exactly, but I guess you have to accept that because that is what the code is saying and that is what everyone is saying. And maybe there is something that we would understand if we go and work in the industry, or if we understand what exactly the requirements are.
Yes, ma'am. Sure.
And then there was that question that you showed, the NPTEL one, which had staggered bolts. So remember the two
Ah.
bolts, three bolts, and two bolts one. So
Yes, ma'am. I do remember.
do you have that in your? Do you have that handy? That picture? If you can show that, I can explain.
1 second, ma'am. I will open up again. 1 second. Give me a 1 minute.
Okay, okay.
Yes, ma'am. Can I share it now?
Yes, I'll stop my sharing. Share yours.
Yes, ma'am. 1 second. Ma'am, are you? Oh, sorry. I think I have shared the wrong one.
I think it was in week 7.
No, not in the week 7. Week 2, I guess. Yeah, week 2, ma'am. Actually.
Okay. Week 2.
Okay. Are you able to see my screen, ma'am?
Yes, it's loading. Yes,
No.
yes, yes. This is the question. So we are being asked to calculate the capacity of this joint. Efficiency of the joint ultimately is a ratio between the capacity of this joint divided by the capacity of the solid plate. So the solid plate capacity we can find easily, and finding the capacity of this joint, one thing was done, that if this is section 1 1, section 1 1 is calculated in a normal manner, right? That what we expect.
Hmm.
Show the calculation.
Okay. Yes. It is
Yes.
calculated only the plate strength.
Yes, that is what is actually, that is what we have to do, because the plate, it is, we are calculating the strength of the plate here, okay? Because the
Hmm.
efficiency of the joint is strength of the plate under the bolted condition divided by the strength of the solid plate. And which plate?
Yes.
The thinner plate, because we are connecting two plates. They can have different thicknesses, but we are always concerned with the thinner plate because that is the one likelier to fail first. So this formula, have you come across this formula? Have
Yes,
you?
ma'am. This is this formula you are saying?
Yes, then point 0.9, if you, this one.
Yes, yeah, this is tensile strength for a plate. Yes,
Exactly.
I
This is
did come
tensile
out.
strength for a plate. So
Hmm.
B is the width of the plate, ND, and N is the number of bolts in a particular section, and along that has to do with the section perpendicular to the load application. So there are two bolts here. So the subtract 2 into 18. 18 is the whole bolt hole diameter, and T is the thickness of the thinner plate, and they divide by the factor of safety to get this. This is fine. This strength of joint 1 1. Now for strength of joint 2 2, you know why we are adding this 2 bolt value? Because see, if last day what we were discussing was that it's a little difficult to perceive that this the force is traveling through the plate, but that is actually what happens. That when you are applying the, did you stop sharing?
Oh,
No,
yeah,
show.
1 second, ma'am. I will have 1 second. Yes.
And show the figure again. Yes, so the load transfer mechanism, see, the load is being applied on these two ends. So when the tensile strength is applied, it first encounters section 1 1 or section 3 3. Let us look at 1 1 first.
Hmm.
Then what happens is that if these two bolts are not failing, the load transfer mechanism does actually happen from one end to another end. It's not, because it is a force that is traveling through. So when, if the section 1 1 does not fail, then the capacity of those two bolts, they transfer that part of the load already to the other plate. because ultimately you have to transfer the force to to the boundary. So that
Can you repeat the last sentence again? Can you repeat that
that
again?
if there are the two bolts, suppose section 1 does not fail, that
Hmm.
means that the two bolts or however many bolts are there in the first section, they are taking a certain amount of stress and
Hmm.
or force, and they are transferring that force already to the thicker plate.
Okay. Huh.
Then
Yes.
the remaining part of the stress has to be withstood by the section 2 2. That is what is load distribution. So the section 1 takes some part of the load, it already transfers it, then the rest is transferred to section 2 2. So when we go to section 2 2, go to the calculation again.
That's fine. Yeah.
When we go to section 2 2, we add 2 into BV because that has already been taken by the bolt. So section 2 2 can take an amount equal to its own strength plus 2 into the bolt value that has already been transferred. It can always take an additional force of the bolt value into the number of bolts in its previous section. Okay.
Hmm. Yeah. Little convincing, but I
Okay.
like, yes, ma'am. But I mean, see, the that doesn't happen only on the one side, right? The both sides, the bolt will be taken. I mean, the section 1 1 and section 3 3.
Exactly. So you
Uh,
have to. I believe that you have to do the calculation from both sides. You have to do for 1 2 3, like
huh.
this has been done. Then you have to do once for 3 2 1 as well. Since this is symmetric, you will get same results.
Okay.
But if there are two,
Okay.
three, four bolts, then you have to do both sides. Okay.
Okay. Then
And
yes. Then yes.
okay. And then there is another thing that I would like to point out. If you would stop sharing, I would show something in my computer. See, in this chapter is sir is teaching bolt so connection, so he has ignored this part. But see, in the design of tension members, design strength due to rupture of critical sections. See, this is where plates are being designed, and this is an exact similar kind of arrangement that we are seeing there. So there is also a kind of zigzag force transfer that you have to consider in this question. Okay, we haven't moved to that part yet. Have you, if you have looked at the lectures further, you may have seen in design of tensile sections, but this is an additional formula here. There we were using b minus n into dh, right? But if there is
Yes,
a
ma'am. In the further lectures, this was covered. Yes.
yes, exactly. So in this question also, whatever what that question that you showed, this has to be included because that I guess that wasn't mentioned in that question because they had only covered up to connections, but this has to also be taken into account. Okay.
Hmm. Yes.
Okay, then I don't think there were any more doubts from previous class.
Yeah.
So I'll
No, from my side.
yeah, okay, fine. So I'll move on to the eccentric connections. Okay, so there are connections can be classified into two: simple connections and eccentric connections. Simple connections are where the applied load passes through the center of gravity of the connections. The connections are the bolts or the welds; they are physical elements, right? So they have a center of gravity, and here the center of gravity is obviously in this plane, it is along this line, and the load is also applied along this. So this is a simple connection. And eccentric connections look like this: applied load does not pass through the center of gravity of the connection. The center of gravity is this, but the load is applied in this, like a distance from the center of gravity. So this is called the eccentricity. Um, this is you have to look in the same direction, of course, along the y-axis. This is the center of gravity, and this is the point of direction of application of load. So this perpendicular distance is the eccentricity. Similarly, if you look at this one, if this is along x-axis, this is the center of gravity, and if you apply a load here, then this distance would be the eccentricity in that case. Connection subject to eccentric shear, there are several types. There is one called seat connection. It is one of the commonest ones. This is a beam. This is an I section beam, and this is an I section of column. This figure helps to visualize how the steel structures actually look like. This is the column. This is the face of the column to which you have to attach this section beam, this beam section. Okay, so we'll use cleat angles or seat angles. They are the same word. This is an angle section. You put an angle here, and you bolt the one leg of the angle to the top surface of the beam, and you bolt this leg of the angle to the column. So these are perpendicular. Okay, this angle is a perpendicular structure, and the beam and column are also perpendicular. So I hope you can visualize how it is being attached here. So this is a seat connection or a cleat connection. Then there is a framed connection where the connection is done on the, again, this is the flange of the beam and this is the web of the beam. Okay, in connection, in column those two terms are not relevant, but in beam this is the flange and this part is the web, and this down again is again the flange. So in seat connection the connections are done on the flange, and in framed connection the connections are done on the web. So again, this is the column, this is the beam that has to be attached. You put an angle here, and the angle has one leg. One, the leg means that angle has a cross sectional area of an angle, and then it has a length. It has a certain length going out of the plane. So this is the length. Okay, this is the length of the angle, and these two are the legs of the angle. They are at 90 degree to each other. So you place the angle such that one leg rests against the column, and one leg rests against the web of the beam, and then you bolt these. You can also weld these ends. So of course it is not necessary you have to bolt it. You can weld this part, this part. Welding you can do anywhere. Bolting generally we do like this. So this is a framed connection, and these are bracket connections. That is where eccentric shear becomes most relevant. The connection here is a little harder to visualize because this is the beam and this is the column, and you don't directly connect the beam to the column. You do it through some external gusset plates. So these are gusset plates. There are several types of gusset plates. One is that when a lot of members, like more than 2 3 members, meet at a certain points to connect it, you put a plate. Because suppose, just imagine you have three eye sections and you want to connect them at the same point. What will you do? You can't connect them end to end. So we put a gusset plate, and we would place all the three sections on top of that gusset plate and bolt them individually to the gusset plate. So they will act as a as a single joint. So here, this gusset plate, what it does, it is bolted to the column, and then it will be bolted to the beam. So it will, and then the force applied will be eccentric. It won't be along the line of the CG of the connections. Bolted bracket connection, they are required at places where the two members to be connected do not intersect each other. The difference between these are here. See, the beam and the column directly intersect, but here the column is going like this and the beam is going like this. So you need some additional plates to join the two. This leads to enhanced eccentricity in both the connection and the member to be joined, and thus structure it is not preferable, but we cannot avoid it always. The bolts in this type of connections are subject to shear and torsion or bending due to eccentric shear. This is important. Torsion comes, we know that torsion is this kind of rotating force. So when you apply the load here, if you had applied the load along this line, then the only force that we have to see is the tension and compression along this line that we have done in the previous, when we were designing bolts or welds. We took the tension or compression along the plate itself. But if you apply the force at a distance from the CG, then this tension, you know that how a force P is transferred here, the P will be there, the P in the perpendicular direction will act as a compression, but P into E will also be an additional moment that the connection has to take. So that is an additional design criteria that we have to look to into in eccentric connections. When the bolts are subjected to direct shear and torque due to shear, then the connection is classed as bracket connection type 1, and when the bolts are subjected to shear and tension, then the connection is called bracket connection type 2. There are two different approaches for analyzing the type 1 connection: the elastic method and the ultimate strength method. We can use any of those. The elastic method is easier to implement, that's why that is the one we study. The in elastic method, the friction between the connected parts, that is the friction resistance, is altogether ignored. Like bearing and shearing type bolts, the bolt, maybe it is tension, it is undergoing tension, there is a normal reaction between the two plates and there is some friction, but we ignore that part. That we are making, see, we have to be careful that whenever we are ignoring something, we have to see whether we are ignoring that on the safer side or not. So the friction is a resistance, right? So if you ignore a part of the resistance, you are approximating the calculation on the safer side. But if you ignore a part of the load, that means you are making it unsafe, so you can't do that. So in the elastic method, the friction between the connected parts is ignored, and the connected parts are assumed to be perfectly rigid with connectors being perfectly elastic. The elastic method of analysis gives very conservative results. Conservative results, why? Because you are ignoring one part of the friction resistance. The See, the results that are on the safer side approximately, they are called conservative, and the ones that are approximated on the unsafer side is are called like they don't exist actually, but conservativeness has to do with safety, and otherwise you make it economical but unsafe. The second approach, the ultimate strength method, gives results that are more close to realistic value, but the method is difficult to apply. Again, see, why do we do approximations? We do approximations, or we create models. They are all based on approximations because they make our life easier. They make calculations easier, and that is also an important part because in a project, time investment also counts. So what the Indian standard codes does is it makes a lot of approximations. It gives a lot higher factor of safety than possibly the than is needed, but it shows the design procedure in a set of steps that are very easy to follow by any layman. So you don't need to be a very knowledgeable civil engineer to design using Indian standard codes. Anyone can do that. So that is why the easier methods are used. IS-800 does not specify any particular method for analysis, so it depends on the discretion of the designer to use any of the analysis method. Generally, the elastic method is used in undergraduate courses. This is the bolted bracket connection type 1. In this connection, the twisted moments in the bolt is in the plane of the connection. So is uh, this is the plate, the gusset plate. This is how the P is applied, and see the twisting moment. The twisting moment here is in, see, the P into AE is applying in this like this, the moment is like this, and the sense of the moment is perpendicular to the plane. This occurs when the line of action of load is in the plane of connection. So the plane of the connection is this. The plane is the xy plane, that the screen that you are seeing is the xy plane, let us suppose, and the perpendicular one is the z1. Then the connection itself is on the xy plane, and the force is also applied in the xy plane. So this occurs when the line of action of load is in the plane of connection, and the center of gravity of the connection in elastic method, or the instantaneous center in the ultimate strength method. This we are ignoring right now, is the center of rotation. So the whole bolt group is subjected to shear and torsion. You know, this is what, if you look at the bolt, if you imagine the bolt, this is the bolt head that we can see the six bolt heads, and the shank of the bolt is going perpendicular to the plane. So and the twisting moment is coming in this way into the plane. So it is going into the plane and out of the plane, so it is along the z direction. So you can understand that that is the same way the bolt has to be tightened, like the bolt is tightened along its shank, that sense. So it is a torsional force, it is not bending moment. Torsional force is the one that goes into the plane or away from, like perpendicular to the plane of action. So the whole bolt group is subject to shear and torsion. The shear is obvious. The P is, when you transfer the P here, this of course shear comes on the bolts. So see what happens is, this is the P, and this is the moment. See, the as I said that if you apply eccentric load, you can shift the load to the center of gravity, and then you have to add an additional moment, the PE moment. So this bolt, the entire bolt group is getting a moment like this. That is what is shown by these arrows. Elastic analysis. The eccentric axial load P is made concentric along with the torque M. So you shift the P to make it concentric with the center of gravity, and you additionally also include the torque, that is P into E naught. E naught is the eccentricity. Let F1 it be the force in the bolts due to direct shear, and F2 the force in the bolts due to torsion. We split the two. The resultant force in each bolt must be less than the strength of the bolt. Obviously, it is assumed that the load on the joint is shared equally by all the bolts, and thus force in any bolt due to direct shear is P by N. P is the P is the total shear that has to be taken by the bolts, and N is the number of bolts. Here there are six, so you just divide the total force applied by the number of bolts. You get the shear force in each bolt. Also, force in any bolt due to torsion is directly proportional to its distance from the center of rotation of the connection. So see that this is the center of gravity, but basically the center of gravity is not the point of each bolt. So if this is the line of application of the force P, then this is the length we are actually concerned with when we look at these three bolts. And we look at these three bolts, we're concerned about E naught plus this R distance. If you this is the center of gravity and this is the R, then when we look at these three bolts, the lever arm that is acting is E naught plus R, and here it is E naught minus R for these three bolts. So that is the torsion that is actually coming. It's not P into E naught uniformly on all the bolts. So F2 is proportional to R and F2 equal to KR. So let K be the constant of proportionality. And the torque about center of rotation of the bolt group is again, the torque itself is proportional to R. So the torque is F2 into R again. So it is K into R square. It is proportional to R square because the torque itself depends on the uh, R, and then the torque about the center of rotation torque, for that you have to multiply with R again. Total resisting torque is sigma k r square. K is the same for K is considered the same for all the bolts here, and sigma r square is the term that we are concerned about. What is the sigma r square? Each bolt will have an r value, minor, negative or positive. This, I think this should be negative and this will be positive, and we have to find out the r square value of each of the bolts and add them. You get r square. So the ultimately the force F2 is maximum when the distance r is maximum. So this is what the formula comes down to be, that F2 is P into E naught Rn divided by, this is the critical one, divided by sigma r square. The two forces F1 F2 act at different angles again, because see, the entire system is undergoing a torsion about its center of gravity. So these the F1 direction is always fixed. It is always along the direction of the shear. So in this case, it will be vertically downwards for all the bolts. But this direction, the sense of the moment will not be the same. We know that it has to do with the tangent of the moment, right? The moment is applying in a certain sense, and the bolt and this torsional force acting on the bolt will be tangential to that action of to this radius. This is the center of gravity, this is the radius, and this is the tangential the line of action of the torsional force. So we have, there is a cos theta coming into the picture. The cos theta is the angle between the two set forces. So if we know that resultant is F1 square plus F2 square plus 2 F1 F2 cos theta. For the connection to be safe, this resultant F must be less than the strength of the bolt. E naught is the perpendicular distance measured from the center of rotation of the bolt group to the line of action of load, which is called eccentricity. R1 to Rn are the distance of the bolts from the center of rotation. Okay, I was wrong about one thing. The R is not the perpendicular distance, it is the radial distance. So the center of gravity is one point, and R is the distance between the center of gravity and the bolts. So R, this is R, like that. N is the number of bolts. F1 is force in the bolt due to direct shear, and F2 is force in the bolt due to torque, and K is a constant. The resultant force F will be maximum when angle theta is minimum, because the cos value decreases as the theta increases. Bolt subjected to maximum resultant force, that is the critical bolt, is the one that is farthest away from the center of gravity of the bolt group and nearest to the applied line of load. So which one will be here? See, all these three are equidistant from the line of application of the force, but this bolt is the R of this bolt will be lesser. This bolt and this bolt are the critical ones, because R is maximum, and the application of and the line and the distance from the line of application of force is minimum. Okay, so this is an example we look at. Find the safe load P that can be carried by the bracket connection. Why is this a bracket connection? You remember that what I said about bracket connections. The Since the column and the beam are not directly meeting, the force is applied at a distance from both the beam and the column. The bolts are of 20 diameter of grade 4.6, and the thickness of the flange of I section is 13.7 and that of the bracket plate is 16 Steel grade is not given. Let us assume Fe410 steel. Now for the bolt grade, as I said, that 4.6 bolt means that the ultimate strength is 400, like 100 into this value 4, and the yield strength will be zero point 0.6 into 400, that will be 240. And the Fu and Fy of the plate material is taken the usual grade of steel, 250 and 410. The stress area of 200 die bolt is pi by 4 d square. And now this is the arrangement shown. Okay, so these are the pitch of the bolts. Like 50 is the, I think, the edge distance, then 90, 90, 90, and then again 50, and the distance between the two lines of bolts is 130. And see, this will be the end distance, but that is not mentioned because that is not relevant. And the from picture, pitch of bolts is 90 millimeter and edge distance is 50 millimeter. Shear strength of bolt in single shear, this is the formula that we have learned earlier. Area into FUB, that is of the bolt, and divided by root 3. Okay, but this root 3 I have not explained earlier. When bolts undergo shear, this root 3 comes from a von Mises failure criterion or something. It has to do with shear. So these root 3s only appear in the shears and never in the tension. It has something to do with the von Mises criterion. I don't know the exact details. And the partial safety factor is 1.25. So this is the shear capacity. The strength of bolt in bearing, again, that we have studied, this 2.5 kb into d into t into fu by factor of safety. This for 20 diameter bolt, diameter of bolt hole is 22 These are listed in the IS 800. These are what that you don't have to memorize, you will be provided with these. Kb is the minimum of these. So this is the value. As usual, we generally see that the bearing capacity is much higher than the shear capacity, so the shear capacity is the critical one. So strength of bolt is minimum of shear and bear, that is 45.26 kilonewton. The highest stressed bolt will be A. So the total number of bolts in the joint is 8. So you divide the direct force by 8. This P, that P we don't know, that P is what we have to calculate. So the force, if F1 in each bolt will be P by 8. And the force in the bolt due to moment, we apply the formula directly. What is Rn here? See, you have to, this is just a geometric calculation. You have to add all these R distances and square them and then take the root. It comes this. This is the sigma r square, and you apply this formula, this Rn. Okay, Rn is the, this particular one, that you have to, the Pythagoras theorem, the base square plus perpendicular square is the hypotenuse root of that. So 130 by 2, this total is 130. So this distance is 130 by 2, that you square. And this distance is from this point, this is the center of gravity, right? So it will have 145 and 190, 90 plus 45, this is the point of gravity somewhere here. So 45 plus 90 whole square, and you take the root. And the square, you square for all the bolts. For this, you can see that for this and this, the R is 149.83, and for these it will be 130 by 2 whole square plus 45 square root. That is what is being done here. And you find the F2 as this. Now the cos theta, you have to, the cos theta is the angle between the two, right? So how you find out, see, this is the theta, this theta. Why? Because if you see, this is the point of this is the direction of application. The direction of application of the shear is vertically downwards, and the uh, line of application of the torsional force is perpendicular to this radius. So we know that the angle between the vertical line and this perpendicular line is theta. So we have learned in geometry that the angle between the horizontal line and this perpendicular one is theta. We know that if there are two lines like these, and then there are two lines that are perpendicular to this and this, then the angle between them will be same, obviously. So this is also theta, and the theta is, we know, tan inverse 45 plus 90 by 130 by 2. So you can find out the cos theta from geometry, and the resultant force is this 0.3471 p. This is in terms of p, because this F2 and F1 will both be in terms of p, because we have just taken it as an algebraic value. So but F has to be lesser than or equal to the strength of the bolt. The strength of the bolt, and be very careful about the units here. We generally work with Newton and millimeter square. Newton per millimeter square is megapascal, that is 10 to the power 6 Newton per meter square. So you have to be careful that what you, so you have got this in kilonewton. So if you got in kilonewton, then don't forget to multiply the by into root 10 to the power 3, or you will get p in, like, just be careful that here if you don't multiply this you will get p in kilonewton itself. These tricks are done commonly in the competitive exams like gate. They will put two options with just with a unit different. So, and in option A they will put the wrong unit, option D they will put the right unit. You see the value you have calculated and you straight away mark A, and then that's a bad way of getting a negative marking even after doing the entire thing correct. So always whenever you are calculating, keep the units, keep putting the units in every step so that you don't miss out anything. And the maximum service load, that this is another, again another important part. In limit state design we have already put the factor of safety here, okay? In shearing and bearing we have put the factor of safety, but we have to put the that was the capacity safety factor. Now this amount 130.39 kilonewton is the design load we can allow. So the service load means the working load, okay? Service load is the design load divided by the load safety factor that we generally take as 1.5. 1.5 is what we apply on dead load, so you can take it as 1.5. We are also, there are a lot of other combinations like in dead load plus live load combination the safety factor is 1.2, but here you can take 1.5. You have to mention why you are taking that. Okay, and this is another question. This is also a bracket connection. Okay, so it is required to design a bolted bracket section for an end support reaction of 350 kilonewton due to factor dead and live load on the beam. This is the eccentricity 185. The eccentricity is 185. Use bolt of grade 4.6. So now this is the inverse problem. That, see what we were doing here, this is an analysis kind of problem because the positioning of the entire connection is given and you are asked to find out the capacity. But here you are given the load that it must withstand and you have to design the connection. So the first example was analysis and this is design. This is the inverse problem. You don't know the connection, you can decide on your own. And while analysis problems always have a unique result, design problems can have any results. It depends on the designer. You can put three bolts at a certain pitch, your friend can put four bolts at a larger pitch. So it's fine so long as your the factored capacity is greater than the factored load. Okay, so let's still here you can decide. See, since the, okay, this has been assumed, the steel grade is 410 and the bolt grade has already been mentioned, so these are all same. For ISBH 200, these are the thickness of flange. These are again in that is handbook that I showed in one of the previous classes. These details will be there. ISBH 200 is a fixed section whose properties are listed in that code. So the thickness of flange is 9 mm. The factored end reaction is transferred to the two bracket plates. Uh, Design load coming on one bracket is 175 kilonewton. So there will be two bracket plates, I guess, one on this side, one on that side probably. So this, I don't think the question is clear enough that you have to divide by 2. But anyway, suppose you divide it by 2. Let 200 diameter bolts be used. Diameter of bolt hole and edge distance. You are deciding on all these. Okay, these are have not been mentioned. The stress areas by 4d square. Minimum pitch. This has been again mentioned in IS code that the minimum pitch has to do with the diameter of the bolt. So 2.5 into d. So 50 is the minimum pitch you have to use. Suppose you are providing 55. So this is the arrangement that you are proposing: 1, 2, 3, 4, 5, 6, 7. 7 bolts on each side, on each line. 55 is the pitch and 33 is the end distance. So, and something here also has to be mentioned: the distance between the bolt lines. Anyway, we'll look at that. This shear strength and bearing strength are calculated the way we usually do, and the shear strength, as is most often, governs it. We provide bolts into vertical rows. Now, okay, the number of bolts are being decided upon here. 6m by, see what they are doing. I, 1 second. I'm not sure where this 6 is coming from. I guess it.
This is like one of the formula is given in IS code. While designing procedure, we start with this.
Okay, do you know why this 6 comes?
Uh,
Does it have to
not
do
no,
with
ma'am, not
the.
exactly.
I think it.
But in the
Okay, yes, sir.
that is in the derivation, but not
Okay.
particularly don't remember right now.
Okay, it probably has to do with the bending stress formula. I have to look into that. And so we 6.25 is, if it's a required, then you have to provide, of course, on you have to approximate on the higher side, because here if you do it 6, it will become inadequate. So we provide 7 bolts in each row. The highest stress bolt will be the farthest one and the closest one to this. So the direct force on bolt A is P divided by 14, that's the total number of bolts, and the force in bolt A due to the torque is, we calculate Rn is this distance. This is 55 plus 55 plus 55, that square, and this distance square, and the eccentricity is 185. So the gauge is this distance, so we assume it to be 90. Again, this is again something you are assuming. I don't think this is mentioned directly. I think some minimum gauge might be mentioned. So Rn will be 3 into 55 square, and this will be 45, because if 90 is the gauge, the distance will be 45 on this side, and the Rn square for each bolt you can calculate. The 45 will remain constant for all, and for 4 bolts it will be 3 into 55. For 4 bolts it will be 2 into 55, and for 4 it will be 55 square. So this is the value, and the cos theta you can find here by this is the theta that you are finding out, and the resultant force you get as 332.78, this, and this is less than the shear capacity. This is the force being developed in the critical bolt, and this is the capacity. So we can so this is fine. Now in design, suppose you had initially decided on something, like you decided on this gauge distance, this pitch distance on your own, right? Just, and the 20 also you decided without any calculation. So it is quite possible that once you reach this step, this resultant force, you find that it is greater than 45. Then you have to redesign it, and to redesign it you have several tools at your disposal. You can increase the bore diameter, you can reduce the pitch, and so on. So this is how we design eccentric connections. And are there any questions? Okay, then next class we will look at design of tension members. Next two classes, I think. And so the lectures of one connection is over. If there are no questions, I will end the class now.
Yes, ma'am. Thank you.
Okay, okay then. See you next week.